Okay, when you pluck a string, a wave will be created that travels along the string. The speed of the wave can be determined using this equation here, where v is the speed in meters per second, t is the tension in newtons, and mu here is the mass per unit length in kilograms per meter. Now that wave speed is equal to wavelength times frequency. So I'm going to put that in that equation there, and I'm going to bring down the wavelength to the other side. Okay, so I get a useful equation for the frequency at which the string is going to oscillate. Okay, normally when you pluck guitar string or any string, you get a stationary wave being produced, and the mode of oscillation or the harmonic determines the wavelength. Normally, if you're not told, you just assume it's the fundamental or the first harmonic, and you use 2 times the length, because that's the wavelength for the first harmonic. Or if it's, for example, the third harmonic, you can use a different wavelength. You can use 2L over 3 and so on. Question, we have a string attached between two fixed points which are 30 centimeters apart. The string is plucked, so the stationary wave is produced, and the tension in the string is 40 newtons, and the mass per unit length is 5.0 times 10 to the minus 3 kilograms per meter. Calculate the frequency of the wave on the string. So I'm going to draw a diagram here, and I've drawn the fundamental or the first harmonic here because the question doesn't tell me, so I just assume it is that one. Okay, and they've got the distance in meters there. So I'm going to write down the equation here for the speed, and of course we know that if we just put wavelength and frequency in there, we can get the frequency equation. The wavelength is going to be 2L. Okay, and so I'm going to put those numbers in: 2 times the length of the string, square root times the tension, mass per unit length, and then you get a frequency of 149 Hertz. Okay, this setup can be used to investigate waves on a string. So what we've got here is a string which is attached to a vibrator and a signal generator, and a pulley over which the string is hanging with a mass attached to the end here. And we can have a movable bridge, which we can form a stationary wave when we set the vibrator on between the vibrator and the movable bridge, and the mass on the edge here provides tension in the string. Okay, in this example, before starting the practical, the mass of a string of length 5.0 meters is measured to be 3.03 times 10 to the minus 3 kilograms. A standing wave is set up as shown above. As you can see, that's the third harmonic. A mass of 0.10 kilogram hangs on the end of the smooth pulley. The distance between the movable bridge and the vibrator is 0.70 meters. Calculate the frequency of the signal generator. Okay, so I'm going to write down the equation for the frequency for a wave on a string. Okay, firstly I'm going to start with the tension. The tension is provided by the mass that's hanging over the edge. Okay, so I'm going to do mass times gravitational field strength to get the tension. So 0.100 kilogram times 9.81, and that gives me the tension there. Secondly, I'm going to do the mass per unit length, okay, of the string. So we know the string has a mass of 3.03 times 10 to the minus 3 kilograms for 5 meters of the length. So if I do that, I get the mass per unit length, mass per kilograms per meters. Okay, finally I need to figure out the wavelength. Okay, so this is the third harmonic, and another length between one point and another. So divide that by 3 loops, times it by 2 to get the wavelength there. Put these numbers in, and you get a frequency of 86 Hertz. Okay, the diagram shows a steel wire. Show that the mass per unit length is proportional to the square of the diameter of the wire here. This question is important because sometimes the diameter of the wire can change. But we're told it's steel, so that means the density is constant. Okay, the mass per unit volume, rho, is constant. Okay, we've got length L here. Okay, and we've got the diameter and area. Okay, cross-section area there, and we'll link all these together. Okay, so mass per unit length, and we know because it's steel and we want density in there. Density is mass per unit volume. Okay, and I'll rearrange that and put that in for mass. So now I've got density and volume in there. Okay, volume is cross-section area times the length of the wire. So I'm going to put that in there instead of volume. Okay, you can see the L's, the lengths will cancel out. So there you go. You got the mass per unit length is proportional to the density times the cross-section area, and the cross-section area of a wire, it's a circle, so it's going to be pi r squared or pi d squared over 4. So if we put that in there, then as you can see, because it's a steel wire, the density is going to be constant, so I can ignore that. Pi is a constant, ignore that. 4, that's it. So you can see density is proportional to diameter squared. Okay, the diagram shows a stationary wave formed on a steel wire which is fixed at point x and y. The wavelength changes from x to y. We can see the wavelength is decreasing as you go from x to y, where the x is where the wavelength is longer, and then you can see y is shorter. Describe and explain the shape of the stationary wave. Okay, so I'm going to use the equation for wave on a string for frequency here. I'm going to rearrange it to give me wavelength. Okay, just swap those around. And the frequency is going to be a constant, and the tension we're going to assume is also constant. So it's actually the mass per unit length which is changing. And the reason for this is because the diameter of the wire is changing. Okay, it's a steel wire, so the density is going to be constant. Okay, and we're going to assume T is all constant here. So what's going on? Okay, so we know that the wavelength is decreasing as you go from x to y. So that's getting smaller. That must mean that mu is actually getting bigger. Why is mu getting bigger? It's because the diameter of the string is getting bigger. Okay, so if the diameter, the mass per unit length is bigger here, so mu is bigger here because it's the cross-section area is bigger, the wavelength decreases up there.